Okay,
How is that?
You're good.
Perfect.
that's much better. And well, thank you. And one more thing. Sasan, are you there?
Yes, I am here.
I will make you a co-host because I have some emergency at home and I need to leave somewhat earlier. So if you could lead the discussion after the seminar, I would appreciate very much. And and Scott, I'm sorry that this is kind of hectic. My wife is in Europe and I need to go home to take care of our dogs. There is some issue. Okay. Anyway,
Yes, of course.
anyway, that let me welcome Dr. Scott Holmes. Uh, he's the chair of cryogenic electronics and quantum information processing international focus team for the international roadmap for devices and systems. And he also plays an important role in our Discover project, working directly with the PI of the project and University of Southern California. He's been very active in DARPA project and then earlier it was Air Force and other federal and then also in the industry. Dr. Holmes received his bachelor degree from MIT and graduate degrees from University of Wisconsin at Madison. Okay, so Scott, it's all yours. I think we have quite a nice crowd now. Let me see how. Yeah, we've already have like 20 people. I believe we can start. Let's say, well, we can wait maybe one more minute because people chip in. And again, this is the first seminar in this semester, and the next seminars will come as always on Tuesdays, first Tuesdays of the month at 3 p.m. Eastern Time, noontime, West Coast, California time. So I will try to, if any of you has any suggestion of an interesting speaker, please let me know, and I will be trying to do my best to incorporate your wishes. I will actually very much welcome any suggestions of interesting speakers who could contribute to this seminar series. Okay.
Okay, well, I think I'll just start with a comment that this is going to be an overview, is intended as an overview. And I'm covering a lot of material. And if your favorite material is not in here, it's not because it's not important. It's because I had so many things to cover. There's a lot of stuff to do in this area. So can I get started?
Yes.
Okay. So I'm going to be talking about in general a technology roadmaps. Where do we need to go and when and that sort of thing. Let's see. Oops. I do have an abstract and information in the presentation that is already uh, let's see. That was already in the flyer, but that's for reference. I'm going to be talking a little bit about motivations, more about superconductor electronics, and most about superconductor electronics, then a little bit at the end about quantum information processing. So why are we doing this? Well, there was a time, this was about 10 years ago when we were even over 10 years ago when I was supporting the government. We were looking at some problems with just the amount of energy usage that's going into computing. And even then, it was clear that the amount of energy was just getting huge. And the number of solutions, for instance, this data center that Facebook was building um, in Luleå, Sweden, um, uh, there weren't a lot of places like this where you get some free cooling and they have a river with excess hydropower, and it looked challenging. That situation has not really changed. Now, it's not so much Facebook these days. It's AI, machine learning, uh, things that are gobbling up the power. But it continues to be a serious problem. So, yeah, we got a problem. And at that time, it looked as though superconductor computing was promising, and we were able to sell a program, so-called the C3 program, cryogenic computing complexity, that on paper looked like could have some significant benefits, especially in power and size. And the big problem that we had with that program was memory, and memory continues to be a problem. So the need is still there. Solutions are still waiting. Um, there have been developments such as D-Wave. They still have the most complex in terms of Josephson junction count, little over 1 million Josephson junctions on a chip in their quantum processing unit. And there are many other companies that are working in this general area of quantum computing. Examples, Google, and you've seen things like this, where there's lots of wires going down into the cold space, and we really need to replace those wires with something else, with circuits down at cryogenic temperatures. And we think that that's a big potential application for superconductor electronics. I'll talk more about that later. The vision is that eventually there will be a hybrid of technologies, whatever works best. And there's going to be a combination. And we think that it's quite possible that some sort of superconductor electronic processing can be a part of that. However, how much a part of that depends a lot on this audience, how innovative we are, and how much we can do to create solutions. So, roadmap. There is something called the IRDS CEQIP report. This is the International Roadmap for Devices and Systems. This is something that took over from the old ITRS, International Technology Roadmap for Semiconductors. Now we no longer care where the solutions come from. They can be optical, superconducting, semiconductors. It doesn't matter. We need solutions. And I lead an international focus team on cryogenic electronics and quantum information processing. And the 2023 report is currently available online. 2023 included I'll say the coverage that we include: superconductor electronics, which I'm going to be talking mostly about in this talk, cryogenic semiconductor electronics, I'm going to skip, and I'll talk a little bit about quantum information processing. And in the 2023 report, we had the first roadmap for superconducting quantum computing. And we're still hoping to work on one for ion trap quantum computing in the 2024 report. However, that's outside of this talk. And so examples of what we talk about: superconductor electronics. This is the section on superconductor electronics. And we start with applications and market drivers. So the new roadmaps, the roadmap IRDS is driven from the top down, meaning the demand, and then from the bottom up, sort of what we can build and new circuits and devices and methods for doing computing. So in the 2023 report, the biggest area of update was quantum computing that has become really a driver for what we are doing. Present status. So we survey the technology, and then we also talk about active research questions and roadmaps. Here's just an example of figures different. These are devices for switching, and they're switching devices, they're memory devices, and we just monitor the status of these things. And we talk about what is needed. Okay. Status summary. It's still developing technology. It's just got a small market, big promise. Quantum information processing is an emerging driver. Logic, there's many competing approaches. I'll talk more about that. Memory, little available, no clear solutions. I'll talk a little bit more about that. And then fabrication, there's research mostly and some commercial fabrication. Key needs, there's a lot of them. Power supply, we really need a better way to supply our circuits. Sensitivity to magnetic fields, currents, trap flux. We need to reduce the area. Logic, memory, fabrication for scale, testing. EDA, electronic design automation, design is also a need, but it's not on this list. It's a little bit less than of a need than some of these other areas, but it's in there as well. So logic, we're still searching for a winning combination. This is similar to our current status, is similar to semiconductor logic families, maybe back in the 1960s, where there were a variety of logic families all competing, and all of them had advantages and disadvantages. By the 1980s, that had come down to late in the 1980s, CMOS won out. And our situation for superconductor logic 2010, this is even now 2020s. We've got the situation where there's many different logic families, including some new ones, and it's not clear which one is going to win out. And what we do is monitor the considerations. We're trying to guide people towards logic families that have the most promise. This is an example table, and what this is showing in the red is that the number of devices per ampere, when you're less than 10 million, 100 million junctions per ampere, that tells you that it's not going to scale. So these are all like the DC powered approaches. Mostly the DC powered approaches we just don't think are going to scale. And then there's other things like transformers and clocked gates and things that we're looking at as well, and the variety of devices. We're still working on how we present this, and there's a need to separate the logic from the power delivery. Right now, these logic families have assumed power delivery approaches with them, and we really need to separate them out because there can be logic that with a better power delivery approach would scale better. But we still haven't found what I consider to be the CMOS for superconductor electronics. Okay, memory. We also monitor memory. The numbers are really small. These are bits, and the numbers are very small. We really need a better memory solution, and there are prospects. I'm not going to cover them here today. benchmarking and metrics. We do look at the benchmarking and how we can compare against other competing technologies. For instance, we look at commercial approaches for refrigeration and how that scales with temperature and with size. So, and we have ways for comparing against cutting edge logic approaches. There aren't a lot of advantages for superconductor electronics unless you have to operate cold. If you have to operate cold, as you do in a quantum computing environment, then there can be significant advantages. The real advantages, I'll just skip through here, is that you really get huge advantages over conventional technologies when you include the interconnects. So interconnects greatly improve things, and especially, well, that over distances. So, of course, interconnects are the big win. Let's see. We monitor fabrication processes. And this is just an example of this, most of the characteristics. We have a little bit of commercial fabrication, and but there's only for 300 millimeter, there's a few 200 millimeter fabs, and then for 300 millimeter, it's just exploratory work that's being done. So there's needs for development there. Let's say we have a roadmap. This needs to be updated. I think the key thing that we're looking at is the wafer scale. Right now, the largest fabs are using 200 millimeter wafers, and the question is, when do we go to 300 millimeter for commercial foundries? And I think that this 2028 is zooming up on us, and I don't think we're going to make it. Maybe, but I don't think we're going to make it, and we're going to have to reassess the our roadmap. Okay. So for superconductor electronics, as far as the technology roadmap goes, applications, small market, big promise, QIP is a driver. We need, the large scale applications are still far in the future. We are at such a small scale that we need stepping stone applications. And it's possible that quantum computing support applications could be those first key applications. Logic devices, we're still searching for the winning logic family. I'll talk more about that in a bit. Memory devices, we need better solutions. I'm not going to talk about this presentation. Architectures, we have some design tools that are helping to accelerate exploration, but we need some tools for logic, such as SNNs. Those are spiking neural networks. Fabrication technology, we have some commercial and some research. There's been slow progress. I think we really need a winning fabrication process, something that can scale to smaller sizes and much denser circuits. And there are people working on niobium nitride, niobium titanium nitride, for instance. I'll talk more about that. And okay. That's sort of the situation where we're at as far as the roadmap. I want to step back and talk a little bit about superconductor SFQ logic, how it works, and that as sort of a platform for where we go from here. Basic introduction, we've got the Josephson junction, we've got two superconducting regions, They've got these Cooper pairs in them, and the Cooper pairs can tunnel across the barrier if there's a phase difference. Now, this is a standard Josephson junction. Okay, current phase relationship. As the phase goes up, it's a sinusoid. So you get more current up to a point, and then it drops and goes through a sinusoid. Okay, so if we're at some point, we can bias these things so that there's some point, and if some current comes in, it can kick over the top and change the phase by, it should be 2 pi. Well, it'll change the phase, and then that's a switching event. So voltage phase relationship. And so there are analogies for these. Pendulum with damping obeys similar dynamic equations. If you're a physicist, you can look at these equations and say, I can see the analogy. If you're an electrical engineer and you're not used to thinking of pendulums, it's a little bit harder. But that exists. Okay, so there's pendulum, and it has to do with the torque and you can look up, there are plenty of people who talk about this analogy. I created a second analogy that it's like a Josephson junction is like a baby drinking milk. Now this is this is a shunted junction. Okay. You feed the baby too fast and it spits up. So if you have a junction, you put current through it. It's like the milk going into the baby. If the current is low enough, no problem. Everything's happy. If you try to put too much current into the junction, then it spits up. And I like the analogy because it gives you the direction of the current that comes out of this thing. Anyway, Josephson junctions, you can shunt these things. And here's the basic Josephson junction RCSJ model. And the problem with these is that they have this hysteresis. And that doesn't work well in circuits. So they can get stuck. You can shunt these things, and then if they're roughly critically damped, then the hysteresis goes away. They switch, and then they come back. So, and you get a little voltage pulse out of these things. Okay, so how are we going to use these? Well, you can make circuits. And in these single flux quantum circuits, because they're quantized flux, that means that the current times the inductance has to be on the order of a flux quantum for circuit operation. So sometimes we're a little above, sometimes below, but we're on that order. And there's a switching energy. The larger the critical current, the larger the switching energy. And if you want to decrease the current, which makes it more energy efficient, it requires increasing the inductance. So there's some trade-offs. Also, if you decrease the energy, the switching energy, if you get too low a switching energy, then you're susceptible to noise. Okay, so challenges, fan out, you get one single flux quantum. If you want more, then you have to add splitters. So there's low gain and low isolation. And there are alternative devices that are being explored, but primarily I'm going to focus on regular Josephson junctions. How do these circuits work? I'm going to show an example with this sort of circuit. Here we got a circuit. And when we're looking at this is like if you're looking at an integrated circuit. and you're looking at it sideways, so that like this is one layer of superconductor, and you've got like a junction between that and a top layer. And between these two layers, you've got vias, and in this case, they're junctions in these vias. There are no direct connections. So we're looking sideways through the integrated circuit, and it creates these loops. Okay, and there's different in an SFQ circuit. We've got different blocks. I call it transfer block. I don't show how that works. That just transfers the SFQ pulse down the line, down the change. You got a storage block where you can store an SFQ, and you have a decision block. And you've got these three key blocks, and that's what you use to make circuits. Okay, so the first thing you do is you apply a bias to like this loop here, this transfer block loop, and the current comes down here and it splits according to the inductances of the two branches. And in this case, if it comes down in the center, the branches are equal, so the current splits equally down these two branches. And that biases these two junctions. Okay, so we apply an SFQ pulse and to the input, and depending on the inductance of the input, there's some current that's going to flow in this loop. Okay, now in this case, we've got a current here and the bias current, and they combine so that it exceeds the critical current of the junction. So when that happens, and in the baby analogy, the baby spits up. And so the current is coming down this way, it spits it up right back the way it was coming. And there's a voltage pulse, and this voltage pulse will shut down the SFQ in this loop, and it will create an SFQ in this loop over here. Again, the currents and the inductance, the current will depend on the inductance in this loop. So when that happens, current gets shut down here, current transfers into here, and now we have all the current, from the SFQ in here. And now in this case, the currents are in opposite directions for the bias and the loop current for the SFQ. And this junction is now happy. It's below its critical current. But this one over here exceeds its critical current, so it switches. Again, when this voltage pulse will shut down this SFQ current here and transfer it over here and create one over here separately. Okay, so now we've got a loop current over here, and these two currents are in opposite directions. This junction is fine. This current is small enough because the inductance is big enough that it's below this junction critical current. So neither junction switches until we supply a reset pulse, and it comes down the clock line, and there will be a current that comes down through these two junctions. And in this case, this junction switches first because it's got these two currents exceed the critical current of the junction. It switches. And again, it shuts down the current in the storage loop, transfers out, and we have an SFQ pulse at the output. So that's case one, where we have a junction. We had a current in the storage loop during the clock. Now, case two is what happens if there's no SFQ, there's no flux quantum in the storage loop when the reset pulse comes. Well, we got the current. In this case, of these two junctions, J2 up here switches, and that shuts down the current, and we get no output, false. So that's just a basic, a review of, or an overview of what's going on in SFQ circuits. We got these loops, we've got inductances that are important, and we've got junctions and critical currents. Critical current.
Start the recording. Oh,
Okay.
sorry. Go on.
Okay. So let's see. Okay. So SFQ logic families, there are, or the implementations. There was the original RSFQ that used resistors, bias resistors, to distribute the currents. Those dissipate enough power that they can be a problem, and that limits their scalability. And there are other approaches. These are just a couple that are more scalable. And there's AQFP, there's other logic families. This one operates a little differently from what I showed. The point here is that there's other ways to do this that have some similarities and some differences. Okay, so what needs to be done? How do we get there? One example is we can look at a gate set. Let's see, did I? Okay, I'm just going to look at a gate set example for one particular logic. This is AQFP, and over time, people have been improving the gate set and making it smaller. And the question is, where are we and where do we need to be? Okay. So this is an example from 2015 to 2020, went down by a factor of 4. But if we look at comparison with CMOS, here's the AQFP examples. And this is where CMOS is. It's like a factor of 25,000 in 2020, smaller CMOS was. Now, if we go back to where we were, about the same, if we look at where we were at the same feature sizes, then it's only about a factor of 60. But still, there was a factor of 60. And so one effort that we were one way to improve things is to figure out how to make smaller gates, smaller, let's see. And if you look at these different, now these are CMOS NAND devices, and compared to AQFP, there's a factor of, well, there's the factor of 60, is that just the way that we do things is less dense. You can get much greater density with CMOS. So we need to figure out, well, why is that, and what can we do to reduce the problem? Yeah. Before we can, yes, you can scale things down, but we can also just figure out why our logic is less dense and see if we can make it denser. And there's multiple improvements of multiple approaches. Moore's original analysis was that there was a contribution due to die size. There was a contribution due to dimension reduction. And you can see there's like 1/3, 1/3. And actually the most improvement was for device and circuit cleverness. And we definitely need to work on that. Okay, so there are a variety of approaches for that. We can increase the number of wiring layers. We can reduce the inductor size or get rid of inductors. We've got interconnects between gates that we need to work on. Right now, the PTLs are huge, like on the order of 5 to 10 nanometers, 5 to 10 micrometers in width. They're huge. We can also work on the JJ size. So there's a variety of things that we can do. Let's see, and these are being worked. One example, junction scaling. I've been saying for a while that these niobium-based junctions are almost good enough, but not quite. And they have some serious problems. And we really need to find a way to increase the temperature limits, become compatible with CMOS back end of the line processing, and to make smaller switching devices. One possibility is either niobium nitride or niobium titanium nitride superconductors. They've got a higher TC. They're compatible with the back end of the line temperatures. They need development. I'll just skip that. Another thing is another area that we're looking at is the power supply. And one of the problems with the DC current supply is that right now we use DC supply current to bias JJs. Here's the current phase relation. And, without any bias, it would sit down here. The junction would not be directional. It would operate the same in both directions and not well. So we bias it so that when a flux quantum comes in, it kicks it over and we get a switching event. But we're supplying current to the circuit. And if we look at the mathematics of these things, we have roughly critical currents of 100 microamperes. And if you have 1 million junctions in parallel and that you've got a bias, you're on the order of 35 amperes. Now, this is assuming that half of the junctions are biased. But these numbers, 35 amperes to a chip, is just impractical. And 1 million junctions is not nearly enough. So traditional DC biasing will not scale. We really have to move on. AC powered logic, there are approaches. This is one that uses AC logic. It's pulse conserving logic. It's from the group at IMEC, the HERS, Quentin and Anna. And it looks very promising. And they've got some stack ups and they've got some proposals for how they would do this using a zero order resonance. They'd have a resonant network of capacitors and inductors to supply this. And to do this, they're going to need these metal insulator, metal capacitors that are that there would have to be added. These have not been, capacitors have not been common in superconductor electronics, for digital superconductor electronics. And so they're working on those. That looks promising. But the question is, who's going to provide this wonderful stack up? Who's going to provide the fabrication for this? And we do not yet know. There is work being done, for instance, at Albany. New York Creates and has some DOE funding along with the IMEC group to work on fabrication, but it's still not clear who can do a stack up. Okay. And we really need demonstrations of these interesting circuits. So, but that's an AC powered logic that looks promising. Another one is what's known as superconducting sustainable ballistic fluxon. This is coming out of SEEK and other and affiliates. Oleg Mukhanov gave a presentation at UCAS a year ago. He gave an update at Applied Superconductivity Conference. It sounds great, but we need a publication with the details so we can look at it and start to add these things and really check them out and see how they apply. Sounds interesting. The concept is that you supply single flux quanta as they are needed to a circuit using an AC power input. And but it's going to require some changes to the logic. We need details. Other things that are being worked on is phase engineering. That's what we're doing with single flux quantum logic. And so we are phase engineering. There's different ways to do it. It works differently for different kinds of Josephson junctions. And it is potentially possible to compact these with some new junction types. So here's the traditional 0JJ current phase relation, because the energy of this junction is zero at zero phase. In the ground state, it likes to just sit at zero. Now there's something called the pi junction. There's a variety of ways to make things called pi junctions. One is with a ferromagnetic barrier layer. And the pi junction is flipped or phase shifted current phase relationship. And the energy is minimum at pi. And so it wants to have a phase shift in the zero state. So you can use these, maybe a combination of these two things, to provide some phase shift, some bias. And there are concepts for doing that. And then there are concepts for junctions that would have more behavior that would allow you to combine more of these things together. The problem is the fabricability. We don't know how to fabricate these things well at all. Even pi junctions are not as well figured out or as fabricable as the standard zero junctions. So yes, there's some interesting ways that you could either use different junction devices or to combine styles, but fabrication is a question. There can be benefits. People have shown that there's potential benefits from going from zero junctions to combinations of these junctions. This is a zero junction, a pi junction. And that should reduce the amount of bias current and possibly allow you to make smaller circuits if you could make these devices small. Pi junctions, there are people working on how to make pi junctions. And I'll just say that it's in progress. One challenge with a pi junction is that when you cool it down, it's going to go, let's see, I'll go back. Here, when you cool it down, you don't know if it's going to have a plus pi or a minus pi phase shift. So that's a challenge with using pi junctions. And there are people who've been working on some way of making a diode. And if you create a Josephson diode in conjunction with a pi junction, maybe that would work to have a defined direction. So there's device work that can be done. And people are working on new devices, new materials. This is an example of a combination of 0JJs, pi JJs. This is work from people in the Discover group Sasan and Masood Pedram. And this is a stack up showing, now this would be a 0 junction down here. This is a pi junction up here, and combinations of 0 junctions, that's the blue, and the pi junctions in pink. And you can make some interesting circuits. And they can be very compact because we don't need the inductance from the circuit. Very interesting. We've got to figure out how to make 0 JJs and pi JJs together, and we're working on that. These, however, might still, while the supply current goes down, it's still only a factor of 10-ish, and we need more than a factor of 10. However, I mentioned this SSBF, this ballistic fluxon, this fluxon supply circuit. So possibly these circuits are compatible with this SSBF fluxon supply, and we can combine them and we'll have a killer logic implementation. Don't know yet. And the question is, how do we fab? Yeah. So there are digital alternatives to single flux quantum. AQFP is one. It has advantages and disadvantages. Some of the disadvantages, large area, has used transformers. They're working on using capacitors and other approaches. XSFQ uses asynchronous cells. There's temporal logic. QPSJs looks very interesting. They've got voltage-based, they're voltage-based nanowire devices. The question is, can they be made? And then there's people are working on gated junction devices. And again, the question is, can they be made? The key thing here is that there are alternatives to SFQ, and people are working on a variety of approaches. And here's another thing that we can do is to look at the clocking. Right now, most of our logic is fully synchronous. It's clocked. As I showed with the example, you have a gate. It requires a clock, and the challenge with this is that within all of this cloud of logic, you have to have a lot of circuits. You have to add circuits for path balancing, and it has a variety of challenges. So large and complex clock tree, for instance. Well, one approach is to go to the approach that is used for CMOS, where you have clock boundaries, you have clock sections, and then you have a cloud of logic, combinational logic in between the clock boundaries. And that is compatible with the existing design tools, and it allows flexible pipelining. And that has been recently showed. So this was at ASC just a month ago. This was shown that you can do this using XSFQ circuits and existing tools. So that looks very promising as well. Quantum phase slip junctions. I'm just going to say that, typical JJs, you have, here's the superconducting part in blue, that's showing the Cooper pair, and you have currents around this loop, and you have 2 junctions. These are weak regions. And you get single flux quantum when they're switching. Well, there's another approach to doing this where you have a superconductor and you have little nanowires or nanostrips, and you've got a region like an island here So you've got two weak regions, and in between here, so that maybe that should be a Cooper pair. I'm not sure. Anyway, we get a current pulse out of these when they switch, and so they have different behavior. There has been some work on making these devices. It looks very attractive, and the group at Auburn University has been working on these in the past. They look very interesting, but the big question has always been, we need a fabrication process for these, or we need a reliable fabrication process. But it's a very different device that has some analogies, could be very interesting. People are also looking at making neuromorphic circuits, and that's because if you look at biological neurons, they have spiking behavior that's analogous to the way an SFQ circuit switches. And people have been looking at how do we take these types of circuits and do neuromorphic computing. And a nice thing about human brains are tolerant to some variations, and maybe component parameter value variations will be less of a problem for neuromorphic circuits. People have looked at these and, on paper, again, they look great. There's a long way to go to figuring out how do we make the circuits that do the computations that we need. But people are working on it. Okay, so the last section I'm going to cover briefly is quantum processing. This is in the roadmap report. Again, we cover applications and present status. Quantum computing, I just want to let you know that there's a variety of approaches to quantum computing. Superconducting quantum computing is just one of them, and there are advantages and disadvantages for each. So one thing that we did was to look at one particular approach, the superconducting quantum computing. And here you have a system overview where you've got qubits, and they're down at the 10 millikelvin range. You've got some interface that's going to be in the 4K, 3K, 2K range. And then you've got circuits that can be somewhere between room temperature and 4K. And then you've got the stuff that's going to be just up at room temperature. And people looked at, okay, these chunks, where can you put them, and what are the limitations if you use different approaches? Now they looked at a refrigeration system that had a 1.5 watt 4K power budget. You could scale that up to some degree. But for them, they looked at it and they found out that if you use CMOS, if you took all this stuff, put up at room temperature, and you had a lot of wires down, the limit in the number of qubits you can control is about 1,700. And the limitation was due to heat leak. And if you put some of these things down at 4K and CMOS, then you could get up to 9,800 qubits. RSFQ didn't make any improvement in that. ERSFQ, they showed that they think it could get up to 59,000 qubits. So that's significant increase. And AQFP and these other logic approaches, we need to check them out and see what is the potential. I think it's going to be a lot higher than this, but we need to do the simulations. Okay, so we have a way of looking at what are the benefits or the limits of different approaches to this supporting the quantum computing. If we look at the trends, this is historical number of qubits over time, and so it's been going up. And if we put on here a Moore's law line, it's been going roughly as Moore's law, except there's a couple of points here that that's part of the IBM team has projected, and for the last couple of years, they've hit their projections for the number of qubits. So they're coming off of the Moore's law line. And Google has also made projections. They have a very challenging, that's a really challenging slope. So the roadmap team went with a 2x per year rate for increase and to create the roadmap. The interesting thing is, if you look at the limits for room temperature control, I said that it was about 1,700. Well, that was back in 2020, and we assume that there's going to be an increase in the capability of room temperature controls over time. People are getting better with the wires, the cables, how they're doing things, finding lower power ways to do things. So we assume that's going to increase with time. And same thing for the 4K control limit. That's going to increase over time. But there's going to be points at which these we exceed the limits. And so we think that the external 300K is going to go up to on the order somewhere in the 2026 range. And then we're going to go to cryogenic semiconductors, and then eventually we're going to need to go to superconductor electronics, and that's in the early 2030s. Okay, so we use that to make a quantum computing roadmap, and this is, I won't go into the details of the stack up other to show, yes, we're showing that we think that there needs to be a transition to cryo-CMOS in roughly 2028 and to superconductor electronics in roughly 2032. And the thing about the complexity for these control systems is that at the trade-off, at the handoff, this is let's say 4 times 400 million. So almost 500 million, 400, about 500 million JJs. And that's far beyond what we can currently make. So we're going to have to ramp up a bit to be able to do the handoff there. So that's the message. However, the caveat is that, this was done using something called planar surface codes. There are other ways to do it. I think the qubit support is the same, but there are other ways to get to fault tolerance that will require fewer qubits. And we're struggling with how do we add that to the roadmap. Still, we still see if you can make qubits, they're going to make them. They're going to want to use them. They'll just have better uses. So conclusions for quantum computing, the real key takeaway is that superconductor electronics is key need for superconducting quantum computing. However, it also has applications for other approaches as well. There are probably going to be needs for cryogenic electronics, and superconductors electronics has a huge advantage when operating at low temperatures, cryogenic temperatures. Okay. I think I'm just going to leave, many of you seen this slide before. Catching the wave. The key thing about catching a wave is you've got to be in the right place at the right time. You've got to be ready to go. So that's it. Thank you.
Thank you very much, Dr. Holmes. We have time for 1 or 2 questions. So if no one has a question, I have one question from you. So you mentioned many of the limitations or challenges or opportunities for improving the superconductor circuit, from architecture to circuit device to fabrication. Which one you think would be the limit or would be the killer part for this technology if we cannot solve? Is it architecture, fabrication, or the fact that our Josephson junction are two-terminal devices, not three-terminal like transistors?
I think the logic implementation. If we can't create logic, there are people who are saying, okay, well, we can do logic with superconductor electronics, and then we can have cryo CMOS, either at 4K or some higher temperature for memory. But if we don't have logic that scales, we're dead. And so we have to create a logic implementation that scales to 1 billion junctions. And if we can't get that, we're dead. And to get to 1 billion junctions, if you have big devices, you're going to run out. You have an area problem. So, first we need a logic implementation that scales to tens of millions of junctions, and then we need to make them smaller. So.
Okay. Thank you very much. So is there any other questions? If not, let's thank our speaker one more time. Thank you, Dr. Holmes.
And yeah, this recording will be available, and the slides will be available as well.
Of course, on the Discover Expedition website.
Yes.
So thank you everyone for attending this meeting. Have a nice rest of the day.
Thank you, Scott. Thank you, Sasan. Bye.
Bye.
Thank you.